This is lesson 6.6, part 2. We're continuing to add, subtract, multiply, and divide functions, mainly just the division of functions, and then we will find the composite of two functions. In the last lesson, we left off with multiplication and division of functions, so here is one for you to try. Go ahead and work it out. There will be some factoring involved, and when you're ready, hit play. When multiplying f of x times g of x, you have to distribute the 3x to all three of the first terms and then distribute the 1 to all three of the first terms. So you get 6 terms. Combining like terms, you get 9x cubed minus 30x squared minus 23x minus 4. For the domain, since the f of x function had a domain of all real numbers, because it's possible to multiply, divide, or multiply, add, and square positive, negatives, and zeros. It's all real numbers. And for the g function, we can multiply by 3 and add 1 to positives, negatives, and zeros. So this is all real numbers. So our final function, since we're not dividing by x at any point, the domain would be all real numbers. Okay, continue with your division. For the division, you'll need to factor the numerator, and you can do that with a tic-tac-toe factoring. And we get 3x plus 1 minus, or times x minus 4. So the 3x plus 1s will cancel, and we get as our final simplified version of f divided by g is x minus 4. Domain for this function had originally all real numbers and all real numbers. In the end, it could be all real numbers except for this division. Since at this point we will be dividing by something with a variable in it, we have to find out what would make that denominator equal 0, because that will be an undefined operation. So when x is negative 1/3, the denominator equals 0, and that's not allowed. So our domain here will be all real numbers except negative 1/3, which means we could substitute any x values in here, but we cannot use negative 1/3. Okay, so now we're starting on composition of functions. When we do composition of functions, the notation you'll see will look like this or this. Either one of these mean the same thing. This would be pronounced as g of f of x. What you do to calculate g of f of x is you first find out what f of x equals. When you have that answer, then you plug the answer to f of x into the g function. So let's see what that looks like. Okay, here's an example. We have g of f of x or g of f of x. These two notations mean the same thing. So the first thing we do, you start from the inside and you work your way out. So we're going to say x equals negative 3 in the f function. So when f is negative 3, we have negative 3 minus 5 is negative 8. Then we take that answer and we put 8, the answer for f, into the g function. So since the answer to f of negative 3 is negative 8, we put negative 8 in for the g function. So g of f of negative 3 is negative 8, which is the answer to f of 3, squared. So that gives us 64. G of f of negative 3 is 64. Okay, these are the same functions we were just looking at, but this time we're doing it the other way around. This time we're finding f of g of negative 3, and we will get a different answer. In other words, it would look like this. So you start from the inside and work your way out. First thing we'll do is make x equal negative 3 in the g function. So g of negative 3 would be negative 3 squared is 9. So now we're finding f of 9. F of 9 is the same thing as f of g of negative 3, because we calculated g of negative 3 and found it to be 9. So then we're going to go f of g of -3 is what we get when we put 9 in for x in the f function. 9 minus 5 is 4. So f of g of -3 is 4. This is an application to the composition of functions. Suppose that you go shopping and you have a coupon good for $5 off the purchase of any large pizza. You also get a 10% discount on any pizza if you show your student ID. How much more would you pay for a large pizza if the cashier applies the coupon first? So what we're looking at is, let's say this, we have a coupon function, which is the price of the pizza minus $5. We also have a discount function, which is the price of the pizza minus 10% of the price of the pizza. And we want to know what is C of D of X, and we want to know what is D of C of X. In the bottom case, we're applying the coupon first and then getting our 10% off. In the top case, we're taking 10% off first and then getting the coupon. So let's try it. Problem is we don't have a price for the pizza. We will get the same answer either way, but let's just do this. Let's say the pizza costs $10. Okay, it's going to be a $10 pizza. So if it's a $10 pizza and we're doing C of D of X, that means we're going to take our discount first on the $10 pizza. So D of 10 would be 10 minus 0.10 times 10. 0.10 times 10 is $1. 10 minus $1 is $9. So the pizza now costs $9, and then we can find how much it costs to take our now $9 pizza and take $5 off of that, and it costs $4. So what if we do it the other way? Let's take, we're going to calculate D of C of X, doing the coupon first. So we're going to put $10 minus the $5 coupon gives us $5 pizza. And then we will calculate the discount for our now $5 pizza, which would be 5 minus 10 times 5. 0.10 times 5 is 50 cents. So this would be a $4.50 pizza. So to answer the question, how much more would you pay for a large pizza if the cashier applies the coupon first? That would be this bottom case. If you get the coupon first, you end up paying 50 cents extra. And that concludes this lesson.